This is one of my TRB 2025 presentations. It showcases the work done together with Mehdi Kalantari from BAST, the Federal Highway Research Institute in Germany. The title is Inversion of Asphalt Pavement Properties from Slopes Reported by the Traffic Speed Deflectometer. The background for the work is that the TSD has been improved considerably in recent years, and it is considered to have potential for a project level condition evaluation. By project level, I mean the ability to access the mechanical properties of the individual pavement layers. The motivation for this study is to investigate this project level potential of the TSD with a focus on asphalt pavements. The TSD device is built into a trailer truck with 10 wheels. You can see here a footprint. There's the measurement beam placed in between two of the dual wheels in the rear axle. Here's the drive axle, which is also a single axle dual wheels, and here's the steering axle, which is a single axle single wheels. The drive direction here is to the right. So the truck dimensions are shown here. 0 is here. This is about 12 meters long. And here we have placed the 0 in between the two tires, and it's about 2 meters 20. The beam is instrumented with Doppler lasers that can sense the speed of the target to which they point, and this is done optically. There's a reference Doppler laser at a distance of about 3 meters if we start counting here just where the rear axle is. And what are the TSD reported slopes then? The measured speed at laser eye is collected, and then there's a speed of the truck, S truck, and the calculated slope is the ratio between the speed recorded by laser eye divided by the speed of the truck. Now the reported slopes from the machine are the calculated slopes of each of the lasers minus the calculated slope at the reference laser, the one that is about 3 meters away in front of the rear axle. Here's an example. You have here the pavement deflection along a line that is just below the beam. You can see this is the deflection caused by the weight of the truck, and the circular markers here indicate the location of the different sensors. If we look at the slopes, then the slopes are the first derivative of the deflection curve, and here you can see how the slopes look like just below the truck, again along the same line that is parallel to the beam. This is where the slope is really 0, it's around here, and this is what the reported slope of 0 is from the device, because this reading, whatever it is subtracted from the other readings. So the objective of this work was to outline a TSD inversion procedure and try to obtain mechanical layer properties while considering all TSD wheels, so the entire footprint of the truck, and also account in the analysis for the way that the TSD is reporting slopes. And the second objective is to demonstrate the procedure over a measured data set and provide some partial validation. The methodology is as follows. We start with collecting the TSD wheel loading configuration and intensity, that is the load intensity of each wheel, the laser spacings for that particular TSD, the travel speed when measurements were taken, and also collecting the reported slopes from the machine. The second step is to establish a pavement model where we need to know a priori the layer thicknesses and also assume Poisson's ratios. The other properties, either viscoelastic or elastic, are assumed. Then we simulate the TSD loading in a model and calculate the slopes at the sensor locations and also subtract the reference slope from the others. And that gives us the ability to compare TSD reported slopes with the model calculated slopes. And then we quantify the mismatch error between the two, and we change the layer properties, assume layer properties, we change them in an attempt to minimize the mismatch. Here's a demonstration. Here you have a road section with about 18 centimeters of asphalt concrete over 52 centimeters of unbound granular material resting on a subgrade and also a deeper soil mass. This cross section is referring to a real road located in the southwest Germany, and in the demonstration we had the 320-meter long single carriageway section with very few cracks that was tested by the TSD. The TSD device, the specific one that was used, was a BAST TSD device called the MESAS. It has 11 lasers. When the truck was traveling over the section at a constant speed of 70 kilometers per hour, and we used the slopes that were averaged every 10 meters. So we have, in fact, 32 sets of slopes. Here's an example. I'm showing here the laser offset in millimeters versus TSD reported slopes. And you can see here all that in every offset there are 32 different readings. This marked or red circles in the center denote the average. If we look at the same laser offsets, but now we look at the coefficient of variation in absolute terms, it is quite clear that as we look at laser offsets that are further away from the rear axle, there is an increase in the coefficient of variation in absolute terms. In terms of modeling, so we take the actual pavement system and then we model the top layer, combining all asphalt lifts into one layer that is 18 centimeters thick. This layer is considered viscoelastic or linear viscoelastic. The unbound granular materials are the unbound granular material layer is split into two. One is the top part with 22 centimeters and the bottom part with 30 centimeters thickness. And then the subgrade and deeper soil mass is split into the top half a meter and then the rest is semi-infinite. While the asphalt concrete is linear viscoelastic, all other layers are assumed elastic. Here's an example of an optimal match. I'm showing here the laser offset versus the slope. And here you see the measured slope or the TSD reported slope in a hollow circular marker, and then the calculated is placed inside or near it. It depends on how the model is able to reproduce the results measured. And here is one example. We have 32 individual matchings like these. As for the results, we'll start with the top layer. The top layer, the linear viscoelastic layer, we were able to back calculate the asphalt concrete creep compliance. This is a chart showing time versus the creep compliance in a log scale. And the solid line here is the creep compliance. That is an average of all the readings. And here you see the dashed lines are encapsulating the range of results that we receive. This is the minimum and this is the maximum, and here is the average. In terms of the other layers, the top part of the unbound granular material, we're able to get a modulus of 356 megapascal. The bottom part of the unbound granular material, 51 megapascal. The top part of the subgrade, 208. And it was practically impossible to get consistent result for the semi-infinite layer that supports the entire structure because the back calculation algorithm tended to generate values that are unrealistically high. In terms of coefficient of variation, you can see that the coefficient of variation of this layer is 37%, and this one is 39%, and then 56% for the top part of the subgrade. So just to summarize the findings, the inverted asphalt concrete creep compliance, the curve looks reasonable. However, it wasn't possible to match it with lab measured creep compliances. And these were measured over cores taken from the road, and after matching the temperature conditions, it was still impossible to get the same result. In terms of the inverted modulus of the top part of the unbound granular material, which was 356 megapascal, this seems reasonable to us, but we don't have any validation data or independent measurement of this modulus. The inverted modulus of the bottom part of the unbound granular material was a 51. It seems to us to be too low, but again, we don't have any validation data for that. And the inverted modulus for the top of the subgrade, which was 208 megapascals, seems reasonable. Again, we don't have any independent validation for this number. The inverted modulus of the deep soil mass, the semi-infinite part, gave unreasonably high values, and it was just impossible to get something consistent or meaningful. So just to conclude, quantifying the moduli of deep layers, so far as we can see, it is unreliable. One reason for this would be that the coefficient of variation of reported slopes increases with the laser offset. We also saw that the coefficient of variation of inverted moduli increases with depth, and the deflected surface that I showed earlier under the track is never zero. And since we are looking at interpreting only slopes, there's actually no practical way of finding out the deflection, the absolute deflection. In future studies, it is recommended to make several TSD passes at different speeds and different temperature conditions to improve the ability to back calculate or infer the viscoelastic properties of the asphalt concrete. And it is also recommended that we find ways to independently validate the approach with measured layer properties that are coming from other sensors or from other measurement techniques. Thank you.